tree. So the height of the tree can be defined as, this is, level. Well, if you look at it, this is 2 to the h minus 1 nodes in this tree, maximum full tree, right? And when you're building a tree, then, in order to arrive at that picture from this picture, then what you're going to want to do is do something. The trouble here is you don't know the order in which these are going to arrive. So notice that in particular 4 is not coming first, right? So if 4 came first, and then 2, and then 6, and then 1, 3, and 5, and 7, then just the naive implementation of inserting a value into the tree would be would generate this, right? But that's not what we got. So what we have to do is come up with another way of keeping this tree balanced as we insert elements into it. So going back to this list, so if I have a 1 here and I get a 2, then there's 2, and I could maybe draw that as a 2 and a 1, but it doesn't matter, so we don't have to make any changes there. But if I come now with a 3, then I would want an algorithm that allow me to rewrite that as 2, 1, 3, right? And I mean, that's the basic thing. And the concept, there's a number of algorithms for doing this. The two that I think are maybe the most famous are the ABL and the red-black. Or in my case, red-blue, because that's what the color of the discs I have for doing demonstrations. But anyway, so what you typically do is you find a pivot point, and then you do what's called a rotation, where this gets rotated down to here, and so on, and then you have everything pointing at each other. And you can rotate, so for a little more complicated picture, let's do this one. 2, 4, and 3. All right. So, bad choice. Let's do this one. 3, 2, 1. So suppose that they, yeah, let's pick 3.5. Suppose they came in the order so that this was the naive insertion algorithm would generate this. Because let's face it, when you're inserting stuff, that's the first thing you're going to do is use that naive insertion algorithm. Does everybody understand what I mean by that? How that works? You do at each node in the tree starting at the base, you decide whether to go this way or that way until you get to a point where there's not a node there and you haven't found your entry, or you don't care whether you found your entry or not. You just say, wherever there's an empty space, we'll stick it there, right? And that's okay because just 2.5 falls between 2 and 3. If it didn't, if it was on the other side of 3, then it would have come out here, 3.2, right? And you wouldn't have gotten down to 2. So you see that? Anyway, whatever it is, you use that algorithm for finding the place that you would naturally put it there using the normal insertion algorithm, right? But then you start looking at things and you say, okay, well, let's look at the height of stuff, and can we live with it? So the height would be, say, 1, 2, 3, 4, and this one would be 3. So one thing to notice is things at the same level, right? So let's put in 5, and then 2 and 5 are at the same level in the tree because they're at the same height or the same depth, depending on how you want to look at it. And so what you're gonna look at, let's get rid of that again. So what you're gonna look at is that we have a 3 here and we have a 1 here. And that the 3 is on level 3 and the 1 is on level 1. And you might decide, well, that's too much of a difference, right? So can we have an algorithm that will take this tree and do a rotation, what the algorithm is called, do a rotation that will make a better balanced tree out of this. And so if you look at this, one way to do that is to come up with a pivot point around a 2, and then you have your 3.5 and your 4, and then you have your 2 and your 1 and your 3. And so now 3 and 1 are on the same level, and 2 and 4 are on the same level, and they're only 1 level difference between them, right? And so that's, if you think about it, about the best you can do as far as balancing goes. You're never gonna get, unless you can fill up the whole, you know, if you got exactly this many elements and you can fill up all the levels, you're never gonna have a completely balanced tree. But here we're gonna have a tree that's balanced for all practical purposes, right? So, the AVL algorithm, it generates what they call an AVL tree, which is a tree that has basically this property, that the difference, whenever the difference, after I do an insertion, so I inserted the 1 here, right? So whenever the difference between here and whatever's down this tree becomes more than 2, or 2 or more, then we're going to start looking for a place that we can rotate it, right? And in this case, what you wind up doing is you start here where you just inserted something. You move back up the tree until you find a spot where the left and the right are well, actually, you'd wind up here because the height of this is 0, right? So it's whatever this 3 is, and so the 1. So what you want to, so this is your new point. This is the first common ancestor where there's a difference in height from this side to this side, from left to right, right? So what you do is you back up, and at each point you calculate the height at that node and the height at the other to the right in this case, and keep going until you get a difference that is 2 or more, right? And once you do, then you will have found a situation where, and there's, I realize that there's something to be proven here when I will just make this statement, but you'll have a situation in which you'll have this node in the middle here that you're going to pivot about. And that pivot will result in this picture here, right? So, so that's the grand idea of the algorithm, is that you start here and you work your way back until you find a node where the left and right are not balanced, right? So here at 2, they're balanced because the difference is only 1, left and right, right? Back to here, and the difference is larger, so that is an issue because the difference is 2, right? And so therefore you start concentrating, and when you do the search, then you'll find some place here, and then you'll have 2 subtrees in essence. It'll look kind of like this in a more general sense. So we're going to put a 3 here, and then there's going to be some, they like to draw them like this, a subtree here, and there's going to be 2 here and a 1 here. And the concept is that the height of this subtree is different than the height of this subtree by more than 1. All right, and so what happens then is you've got these, and you might have a subtree over here as well, but you have identified these, let me do something else. Let's put another subtree over here and put the one off down here, off the end of this subtree. Does that make sense? Okay, so anyway, you've got this point, and this point, and you're going to form your pivot around that, and you're also going to use this item right here. Okay, so now notice that the picture that you arrive at is that everything in this subtree here is less than whatever's here. You see that? And we know this is less than that. And also we know that this is less than that. And everything in this subtree is less than this, right? So what you're going to wind up doing is you're going to take, let me put some labels in here, T1 and T2, for example. And I'll, just for grins, put in T3. All right, so what we're going to do is, because this leads back to here, and we've identified this as the balance, or the rotation point, the pivot. We're going to focus on this, and we're going to remember that, and we're going to remember this. And then what we're going to do is we're going to take 2 and we're going to promote it by taking 2 and putting it up here. And then we're going to take 3 and just rotate it down like this. Okay. And now T3 still stays attached to 3 here. But T2 now, it falls between 2 and 3. You see that? Everything in this subtree has to fall between 2 and 3. And so we can get away by putting it right here. Okay, and then everything in T1 then just stays where it is. And T3, and 1 will stay where it is. And that's how you wind up with a sorting of this thing. And so I gotta believe I did this wrong. Oh, I added too much extra stuff on there. Okay, so that's the more general case. The concept here is you're going to just treat whole subtrees as units and just repin them from one or more of these selected nodes, right? Not this one, but one of these two. Okay, and typically, then you have a couple of situations. There's actually 4 situations in AVL that you have to identify which situation you're in. And then there's 2 rotations. There's that one, which is, I believe they call it a left rotation. And then there's a right rotation, which in which it's on the other side. So let's see if we do that real quick, 3.5, and then 4 and 5 and 6 and 2, or 3. Let's just do 3. Okay, so we've added now 6 right here. We have to come up to 4 to find a spot where it's unbalanced. The left and right are unbalanced, and so that will be our topmost point, and then this will be our pivot point. And then what we do is we pivot it by winding up with 3.5, 5, 4, 6, and 3 stays where it is. Okay. So to decide which direction to pivot, you have to decide where you're unbalanced. right? And what is the nature of the unbalancing that you have? And there's four cases that you need to deal with. And they have kind of unique names. There is a left, and a left, right, and a right, right, and a right, left. And the way you distinguish these is when you find your prospective pivot point, the key, this, you know, so maybe we had added 4.5 instead of 6, right? So now this becomes, they call us the key, so this becomes the key. And what we're going to notice is that it is to the right of 5, but it's to, I mean, it's to the right of 4, but it's to the left of 5. So this is a right-left situation, right? And the pivot then kind of goes a little bit different. You have to do a 3.5, 3, 5, and 4. No, that's not right. 4.5, 4, and 5. Right. So you're going to take this and move it down here. You're going to take this and move it, promote it, and then so you're basically pivoting around this guy. And it's kind of a weird pivot, but truthfully, when you think about the pivot, you're pivoting. If you lay these out in numerical order, you know, there's your links, but if you, I can't even do it right. So you have 4, 4.5, and 5. And so that's the original picture. And so what we're going to do is we're going to pivot about the one in the middle numerically. Right? And so that's what these two things do, is they dig deeper and do a little more flipping, but that's basically what they are for their situations. And then there's 2 rotations that you use to get all this done. There's a left rotation, and then there's a right rotation. And this one, you just use a left rotation, and this one, you just use a right rotation. And that's that case, remember, where the number is just in between here. I mean, the pivot is just in between these two. These 2 rotations require a combination of these rotations. Or these 2 situations require a combination of these rotations. And so when you're looking at it, trying to figure out how you're going to, when the algorithm runs, you basically have essentially a case statement to figure out which of these is the appropriate situation that you're dealing with. And then from that, you can figure out one or the other of these, or some combination of these to be done. Okay. Any questions so far? Yeah.
If the tree was self-balancing, would we ever get into the situation where this one went 5, 3, 2, 1?
Right. Not like that, probably. You're right. Yeah. You're right. So let's think about how we might get there. Actually, yeah, no, yes. You would get there. Yes, let me show you how. Let's suppose that the input sequence is 3.5, 4, 3, 2, 1. Okay? All right, so I put up the 3.5, so I'll do that right here, right? And then I put up the 4, so that will go here. And then 3 comes here. And then 2 would come here. Now, the difference between 2 and the levels of 2 and 4, so when you add the 2, you say, okay, let's go find an unbalanced situation. And you won't find one. This is a balanced tree.
Yes, but when you add 1 to it, then
Now I
you
add
balance
1,
it.
so the first thing I do is just do the insert, and that would be the 3 here.
Right, and put 2 in where the 3 is, and then.
That's what this algorithm does, right? That's why you have to have an algorithm to do the rebalancing, to recognize the situation and figure out what to do about it, right? Any other questions?
So which one would you use here to balance the 3-2-1?
For this one, right? I believe that's what you call left-left, right? You go to the left and then you go left again, so you're going to do I believe that's called a left rotation. I keep getting those confused, but I believe it's a left rotation. But either this is the left rotation or this one is. It's one of those. Yeah.
So I have a question, is the situation that you're in, do you identify that by the path back to the, I guess, the balancing point? So here it's from
Yeah.
1, or wait, no, this will be left, so it's from the balancing point down.
Right.
Okay, so 3 left to 2, 2 left to 1.
Yeah, but this is where I could have used more preparation. Sorry, guys, but what I think you do is you use the key, which is the newly added node, which is down somewhere at the bottom, right? Use that key and decide based on the pivot point that you select whether or not, the node that you select, whether or not the key is on this side of the 3 or on this side of the 3. And is it on this side of the 2 or on this side of the 2? And that will help you make your decision as to which of these situations you're in.
Thank you.
Without looking at, if there was some other subtree here, for example, and the 1 was put down here, right? Then you need to recognize what situation you're in here. Yeah.
So, in a normal, I guess, binary search tree, if you have just a value and a left and right, you don't have a parent, right?
That's right.
So you take the newly added node, you go back to the head and traverse back down?
Yeah, good question. The answer is yes, you do, because to find your location, you did the traversal down to where you inserted it, and you've still got all that stuff on your stack. So you're basically what you're going to do is go back to the point where this is, checking the height
difference.
of left and right until you get to the point where you're left and right, and then the parent is there on the stack. So you'll wind up returning the 2 as the head of this tree that you've rebalanced, and it will be assigned at that top level into the left side of this node. Right? Okay. And I bet you would love to see some code.
Hell yeah.
Well, yeah, forget it. That's an exercise for the student.
Do you need airplane?
Yeah.
What's that?
You're switching to airplane, and just clear it up for
Yeah, right. My password is a sonnet. It takes me a while to type it. let's see, so I believe what you said was, I go here, and I go, what was it called, Antones?
Antones, yeah.
It's gonna give me a number? No, it's already done. Okay. So, this is Wikipedia, guys. So you can look this up in Wikipedia and follow along if you want. But, let me see if I can get to, where I wanted to get. Okay, so, right, let's look at that. Let's go back up a little bit higher. Yeah, that's not what I want. So this is what they call a left rotation. So I had it backwards. So the left rotation is going to rotate this 3 up to where the 2 is. Or, yeah, that's not the right one. I guess I erased the right one. Yeah, so the example is one where we have, let's say 7, 8, 9, and then 3, I don't know. And so, and then we add 10. So now we want to rebalance by pivoting around the 9. So the way you pivot is this direction, is how they come up with the concept of a left pivot, right? And so, in this case, yeah, so that's the left rotate. Now, notice that to do this, to pull this off, all you've got to do is identify this link right here, and this link right here, and this node right here, and this node here, okay? And what you're going to do is reconstruct this subtree such that 9 becomes the root of the new subtree, and then 8 and anything that pinned it off of 8 over here. And then 10 in this case, okay? So, for simplicity, let me just get rid of this. So that's the left rotation, right? And this other one that I was showing you here is the right rotation. Same concept, but notice that the big O of doing that rotation, anybody got a guess as to how complex that is? O1, right, because all you're doing is moving some pointers, about four pointer movements, and you're done. So that's pretty cool. However, to find your location where you're going to do the insert, if there are n elements in the tree, right? Like in this case here, there's seven elements in this tree. Then this is equal to n, right? And so we have 2 to the h is equal to n plus 1. And then if we take the log of both sides, we have h is equal to log of n plus 1. Okay, and I said earlier that the number of comparisons that you have to do is the height, which is h. And therefore, this is the complexity of this algorithm, the search algorithm. And that's why binary trees are so nice, because log gets cut down real fast. And so, in typical fashion, when you do big O, you do big O of log n. You throw away the +1, don't care about that. So that's that. Then there's the question of how many of these rotations do you have to do, okay? And it depends on the structure of the tree, but since you're keeping the tree fairly balanced, you shouldn't have to go very, very far up the tree to restructure it. If you take a tree like, you know, this one, that comes out of this one, and don't balance until you get to the end, which is another possibility, then you're gonna have to do rotations back up the tree until you get to a balanced tree. Right? And then there's algorithms for doing that, and there's complexity measures for doing that. It has to do, I forget now, something to do with the number of elements or times log n, but don't quote me on that one. The best thing to do typically is just to keep your tree balanced at all times. It should be all right. It's still possible to get into a situation where you have to do, you know, one rotation and then you have to go check the tree again, keep going back up till you get to the root and checking that. Because if you think about it, suppose I have my root here, okay, and then over here I have a subtree, and over here I have a subtree, and down here I add the new node, the key, right? And when I then follow this key back up to the root, right, I'll check the balance at each node along the way, right? Until I find one that is unbalanced, and then that's where I do my first rotations. But in this case, if you think about it, since I've since this was balanced to begin with, and I've only modified this by adding this one thing, I'm not going to have to do any balancing over here. I just have to do balancing there, unless for some reason it puts me over the top and I have to move that. But still, that's just going to be a simple rotation from over here like that, and then just the height of this gets shoved down. But you see that? Okay. Yeah. So if you look at this code here, which I haven't, they're doing a left rotation. They're going to wind up with Z as the head of this newly formed or newly balanced subtree, and then X will pend off of G, and all of these will pend off of those. And so notice a couple of things. What we're doing is we're taking these two and sticking them onto X, right? You see that? And this one stays stuck to Z, right, for that rotation. And when you're rotating the other way, you'll see a similar pattern. So another way of saying that is all you have to do is, you don't need to modify that link there, you just have to modify this one, and this one. And yeah.
So that does mean, if you go back to your 3, 7, 8, 9, 10,
Right.
you still need to understand 7, because you need
Yeah,
7
you need
right.
to know. Yeah, you need to know this this link right here, because you're going to reformat the point to 9,
Yeah.
right?
So
Yeah.
it's from the pivot, it's parent and parent's parent.
Right. But the main part of the pivot is to restructure this subtree that pins off of J or Z, and when you get, or actually here, pins off of X. When you get done now, Z is going to be the root of that subtree, right? And then that's what you have to supply to the parent. So yes, you have to know who the parent is to do it. But notice that you only have to need to know the immediate parent,
Right.
right?
It can be 20,000.
No other
for
ancestors.
the root, yeah, or for the head.
Right. Okay. So, trying to remember this code here. I don't think I like the way they do it. Let me go back to the code I wrote. All right. So, if I could spell, might be better. Okay, so I'll have to decide if this is a proper right rotation or left rotation. But the main thing I wanted to point out here is just the simplicity of these rotations. There's just it's just a sequence of assignments. And then you're recalculating the heights by just checking them, getting the max of the left height, the right height, and then adding 1 to it. And that gives you the height of the node that you're working in. And so here I have a node that is, let me think about this a moment. This made perfect sense when I typed it in. So this is a node class, right? AVL node. And it's being called so that I can do a rotation for it. And then what it's going to try to do is take whatever the left pointer is, whatever that node is, and let me draw a picture. So it's going to take, so here I have the root node and I have the left node here. And I'm going to refer to that as X. And then whatever this is, I'm going to call T2, and I'll use that later. So I save that off into T2, it's just a temporary. And then what I'm going to do is I'm going to take X, and I'm going to repoint this to, we'll just call this R, or let's call it this. So I point that to this, okay? So this was the original node that I was calling, and I'm saying I'm doing what did we decide that was? A right rotation of this subtree. And so I start by saving this pointer right here, because I'm now going to modify it to this. And I want to take it later and stick it, here. Okay, and so then I'm going to take, and in this notation, this left is where I'm going to assign it. And so then I just, at that point, I'm essentially done with the rotation, because whatever was down here, I'm not going to modify, right? So in particular, this node right here, this pointer right here doesn't get changed. So Now all I've got to do is arrange to have that pointer done in my code. I do that simply by returning X here. And that's the pointer to the root of the newly balanced subtree, right? And then whoever the caller was is responsible for storing it into the left of the parent, where it was where it used to be pointing to this, it will now be pointing to this. Okay. Right. Any questions? How many fully understand this and can write a better piece of code than this?
Did you say there were a couple of different algorithms?
This is the AVL algorithm. There's also the red-black algorithm. The red-black algorithm is sort of similar. It does have its rotations. It works by coloring. It's got a set of rules that it uses to tell you how to color in the nodes in the tree. And right off the top of my head, I don't remember the rules, so I can't really explain that one to you. But when you get to a place where it breaks the rules, then you have to do a rotation, and you have to do the rotation in such a way that it brings it back into compliance. Right. So I'd recommend that, and originally I had intended that today we would go through that one, but I didn't. I ran out of time and didn't have time to prepare that. Yeah.
How are the two different heights kept track of?
Yeah. So what I did first thing to notice is that if I'm building this tree here like this, right, and I built this tree, and that was because I don't have a good example, but suppose I was given a 2 and then a 4 and then a 2 and then a 6 and a 1 and a 3 and I just built this tree, and the tree is there and woohoo. Okay, so now I say, but notice that I haven't done anything to calculate the heights, right? Or even define what a height is here. So you could write an algorithm that you give it the root and it goes through and calculates a height for each node and then stores it in each node. So that means that your binary tree node now has to have a slot for a height. And so you might have a class that has a value, a height, a left, and a right. Okay, so now the way that the algorithm would run then is it would run down the tree until it gets to the bottom of the tree, which means where the left and the right are null, right? And say it would start by saying, okay, well, this is the height of this one is, I don't know, 1, right? Height of this one is 1, because they don't have, or you can make it 0. It's up to you. But then you get up here and you say, okay, the height of this one is the maximum of the height of these plus 1. So that would be a 2, right? And then this would be a 1 and a 1 and a 2, and this would be a 3, right? And if you look at one of these others, let's do a different one here. So let's go back to our good friend 7, and then 4, and 8, and 3, and 2, and 5, and 1. All right. So, and so if you do that, now you just do a recursive descent of your tree. And then as you come off of the calc, you'll calculate the heights. So here we'll start with a 1 and then a 2, because that's a 0, right? So max is 1, so you add 1 to that, and that gives you 2. And then this one is a 0 also, So you get 2 and 0, so that's a 2 plus 1 is 3. And then this one has 2 zeros, so that's a 1. And then this, the max of these two is 3, so this, you add 1 to that and you get 4. And then the height of this one is a 1, so the difference, the max of that is a 4, so this one is a height of 5, right? So now, if I go to any node, I can look, I can compare this, the height of this, of the node in each, to the left and to the right, right? Because they're all labeled. Now, as I modify my tree, I can now relatively easily, because these rotations are so simple, I can relatively easy just readjust the height. I do it here by just saying the height of the original node, original root now is the max of the left and right height plus 1. And the height of the new root is just the height of the left and right plus 1. Yeah.
I think you could zoom in a little bit on the code, it's a little hard to read.
Say again?
Could you zoom in on, or make the.
Yeah, I can do that. I learned how to do that recently. Let's see if I did it. Nope, wrong.
IntelliJ does not recognize Command plus for zoom, and it's really irritating.
That's really irritating.
Yeah, go to preferences, editor, font sizes. There's also a presentation mode under view that might be helpful.
Yeah, okay.
Enter presentation mode, very bottom.
Very, third from the bottom.
Okay, is that better?
Oh.
Is that good enough? Okay, so, right, so I'm thinking I may have named these wrong, but
I think they're.
I'll have to think that through.
I think they're correct, because you
Right.
did, it's a rotate to the right.
Yeah.
is what
Yes.
you- is what
I'm
you-
sorry, I just came in, so I'm just asking, like, what are we covering right now?
We're talking about AVL
AVL.
binary search trees,
Okay,
the AVL rebalancing algorithm. Okay, where was I? Oh yeah, so as you make these rotations, it's really easy and cheap to recalculate the height, to adjust the height, node heights. Because all the nodes down here, you don't have to worry about. They don't change. It's only these two nodes right here that where the height is going to change. Right. Okay, so what else? Where was I? Oh, we were talking about heights. So, yeah, so therefore, the insertion time for an AVL tree becomes the height of the tree, assuming it's balanced, which is log n for the number of elements in the tree, right? And the rotation time is it's a constant, so it doesn't really affect the insertion time, right? So, yay. And then subsequently, if you want to do searches, the search time is the same as the insertion time, it's log n. Right? If you want to do a delete, then after you do notice that the delete's a little stickier because you may be deleting a node somewhere in the middle of the tree, and you have to rejigger the tree to keep it a binary tree and B balanced. So that can get a little bit more involved, but it's actually I don't know. I don't know what the big O of that is. If anybody knows, no, okay. Yeah.
What would be like, I guess, like in practice, when should you reach for as a kind of a self-balancing tree over just a regular non-self-balancing tree.
Yeah, okay. So if you're gonna do a lot of searches of your tree, or for that matter, a lot of insertions, then you're probably gonna want it to be balanced to get the best performance, I would think. Now, the trade-off is this, log in. Well, actually, it's not really a trade-off, because the worst case scenario, if you don't do this, is you wind up with 1, 2, 3, 4, 5, 6, 7, which is a linked list, which has a big O of N, right? For a search or an insertion. What I'm trying to say is you gotta look at your data and see what you think the statistics for your data are gonna be. And off the top of my head, I'm not seeing a reason why you wouldn't want to keep it balanced. But anybody have anything to add to that? No? Okay. I think that's all I got. Unless somebody else has a question. Yeah.
This is the first time I've heard of the ABL. I
Mhm.
usually just know of like breadth first search and depth first search. So
Right.
when you're searching for this one, which direction does it go in?
It's just a same thing. It's a binary tree, so it's a binary search through the tree.
Oh.
So you look at each node, you start at the root, you look at each node and decide, is it less or greater than?
Oh.
And at each node, you make that decision, and that just tells you which direction to travel down the tree.
Okay.
So it's a search traversal rather than one of those other depth first or breadth first search. And the maximum number of, because it's balanced, the maximum number of searches that you're gonna have to do, comparisons that you're gonna have to do, is the height of the tree. Right.
And that's is it log n+1 or?
It's log n, yeah, it's log n+1, but it, in big O notation, we just say log n.
Okay.
When n is big, it doesn't matter. The 1 doesn't matter. That's it. I think that's what I got.
Awesome.
Now, if I could just get this out of display mode.
AVL is actually the name of the people that came up with the algorithm.
Yeah, I didn't know that. I should have.
I don't remember their names or the name, but if you go back to Wikipedia, I'm pretty sure it has it at the very top.
Andy, Vic, and Larry, right?
Right.
Okay, there must be a way out of this.
So are there different implementations that might make trade-offs with space, like storing the total height of the ABL tree and the heights of each node and things like that?
Can you say again?
So I'm just thinking if I were to do like a naive implementation from scratch, like what I want to do is kind of, I guess, the standard naive implementation to let the tree keep track of the height. I guess one of the characteristics of a naive implementation, or a basic one.
Do you have your class definition?
Do I have my class
Yeah,
definition?
but you basically put it up there. I think you've got
Yeah, I
value, height,
actually-
left, and right.
Okay.
It's basically
That's
this.
your basic implementation. Technically, you don't have height, and you basic. You can still determine that based upon as you go through. From
Yeah,
the
so I guess I wasn't following what your question was. Try again.
I guess what would a basic class definition for the ABL tree, which is what you pointed out there. Okay.
I would, yeah, that's the basic, probably the basic for an ABL tree, because of the height.
Would you not want to actually store the height of the property on the tree? You just compute that as you go, or like in
No, you have
the real
to,
world?
you probably want to store it, otherwise you're always recomputing.
Right, you want to store it, otherwise you're recomputing it, but you may, depending upon where you're at, you may not be given. I mean, if you're given a node that you have a tree class or some sort of, you're given, you may not have.
No, you just turn to them and say, I can't work this way. You gotta let me,
Personally, what I would do if I.
gotta let me subclass it.
I'd also add parents, because that will reduce.
Yeah, doing parent would help, yeah. That's true.
Reduce it, because you don't have to go back to the head to come all the way back down. You just go from the node and go parent.
So each node stores its parent. Okay.
My algorithm, what it did was I just returned the refactored subtree
Yeah.
root, and then left it to the caller to store it wherever it needs to be stored.
Okay. Yeah, that's fun. I like this.
Jason.
I am. Hi.
I'm
Hey, yeah. I'm looking forward to your lightning talk. Nice to meet you.
Thanks, George.
You're welcome. And if you want to come to that meetup, cracking the coding interview,
2 p.m., right?
huh?
Sunday at 2 o'clock.
Sunday at 2 o'clock. We also have a Thursday meeting up in Round Rock. About 6 o'clock, I think.
Yes, 6.
But I'm not running that one, somebody else is.
Cool. Awesome. Thank you, George.
Something,
We're doing, I don't know if you noticed, September, no, the October meetup, George.
Huh?
In October, we're doing like lightning talks, and the prompt is like your favorite algorithm, 5 to 15 minutes. If you're interested, let me or Tyler know.
Yeah,
Should be a pretty fun one.
I think it might be fun to do something like A-star or Dexter.
Yeah, that's cool. In like 15 minutes?
Yeah,
Awesome.
of course, you gotta start by teaching breadth first, but
Yeah, I'm doing a really, really weird one, so I think the idea is more to introduce and maybe spark some interest and kind of teach them.
This is what I got here before he started. So ignore the bottom for now. It's me trying to figure out what I would actually do the steps.
program. Program.
In the ABL.
I've done that. I've done that. Right now, I'm working for the video that
Look like.
contact person.
And then these are the steps that
I'm doing the contact person Richardson, trying to find a job that will keep me.
I didn't do I did a point at the top for a reason. Because this one goes here, and this one goes there. So it's not, I didn't do
Everything from senior language to Scotland.
Right? Yeah.
Assembly language, machine language.
I put it in a very sharp manner. I don't know if I can sharp for a reason, so I can. That was basically an actual note.
I fell out of the currency there for a little bit because I got an MBA and I did
When you're on the left right, you're on the right side.
yeah, no, I got on programming product manager.
That way you're in line. Once you're in line, it's like you're going off all the time. It's up to you.
And that kept me away from too much and I couldn't stand it anymore. So the last few years I've had to retrain myself.
Do you know about
I'm still trying.
Oh, yeah.
To follow you from there, you're going to learn the language.
So recently,
You say something and then it becomes wow, or whatever else.
so recently, for example, well, when I left my last language, sorry, the library. And so I did my math. ultimately, I'm deciding.
Either I read this and I don't like it, but you can't have it. I can't read it. So everyone should do those together.
Time to change up the job.
I don't remember which one of them. The other is not true.
So, yeah, I decided one day just to see what cops law. I just applying for a job. Because they had expressed interest. Yeah, when I started my career, I was a language person.
Similar idea. Walk through the retirement that way.
Yeah, that's not
That's why I agree. You rent it until you're big enough. It makes sense to buy a room. It's not bad, man. It's not bad. I heard her say that to me. I said it.
Well, then the owner doesn't have another problem. It's somebody else's problem. They do their stuff, they got to do this. The last 40 years or so, especially some other concepts.
Not quite there yet.
Yeah, I mean,